Recognizing his momentous commitments to the discipline of material science, Kaku has received significant acknowledgement for his focus on the historic potential opened by the James Webb Space Telescope, JWST. This uncommon instrument has accomplished huge achievements, including the revelation of 6 massive galaxies that challenge previously held scientific beliefs. These galaxies were once thought to be inaccessible by current research techniques, yet their discovery offers an unprecedented opportunity to improve our understanding of the universe. What makes these discoveries particularly compelling is their apparent simplicity, yet they quietly push the boundaries of established theories concerning the formation and evolution of galaxies. It is crucial to examine these discoveries closely, as they underscore the vital role that scientific advancement plays in shaping our perception of the universe. Kaku, a highly regarded figure within the academic community, is widely respected for his extensive knowledge of both classical physics and quantum mechanics. His exceptional background, which bridges both American and Japanese cultures, has fueled his strong passion for exploring the groundbreaking possibilities revealed by the JWST. He eagerly embraces the telescope's discoveries, enthusiastically sharing them with the public, highlighting his dedication to broadening humanity's appreciation of the universe. His openness to engaging with these new revelations, which can no longer be dismissed, reflects his commitment to advancing human knowledge. Kaku's distinct perspective shines through in his reflections on the JWST's discoveries, which have reignited his intellectual curiosity. Throughout his career, Kaku has been known for his openness to unconventional ideas, welcoming concepts that challenge long-established teachings. While he acknowledges the significance of Einstein's theory of relativity and Newton's laws in contemporary science, he argues that these theories do not fully explain the complexity of the universe. Kaku contends that the JWST's discoveries may significantly transform the field of cosmology. Although many of his colleagues remain skeptical of this perspective, such skepticism has led to doubts and criticisms, particularly from proponents of the Big Bang theory and quantum mechanics. Nevertheless, Kaku stands firm in his belief that the JWST has uncovered 6 massive galaxies dating back to the early universe, each containing more stars than our Milky Way. These galaxies formed just 200 to 700 million years after the Big Bang. A team of cosmologists has aptly named these remarkable galaxies universe breakers because their discovery challenges current cosmological models. If these findings are validated, they could dramatically reshape our understanding of the early universe, suggesting that its initial stages were far more dynamic and complex than previously believed. The prevailing theory regarding the universe's origin states that after the Big Bang, the universe was chaotic, and it took a long time for the first solid structures to emerge. It was once assumed that galaxies began forming much later. However, the mass of the galaxies identified by the JWST is already larger than the Milky Way, and their extraordinary brightness indicates that they may have been producing stars at a much faster rate than our own galaxy. Conversely, the Milky Way generates stars at a slower, more unpredictable pace. While the precise timeline for the formation of the first cosmic structures remains uncertain, it is evident that the early universe may have started with isolated stars or small clusters that eventually merged into larger systems. For a long time, it was believed that such massive, mature galaxies could not have existed so soon after the Big Bang. This raises a crucial question. Is the universe older than previously thought, or did these enormous galaxies form much earlier than expected? This idea presents a significant challenge to conventional scientific understanding, which still struggles to reconcile these new discoveries with existing models. Some aspects of physics have even dismissed these findings, questioning the accuracy of age estimates. However, Kaku is fully aware of these criticisms and has openly expressed his stance on the matter. He points out that many outdated theories persist due to the influence of prominent scientists, despite being disproven by later research. Kaku insists that true scientific progress comes from experimentalists who focus on precise and accurate theories. He further emphasizes that humanity's understanding of the universe's origins remains incomplete, highlighting the need for continuous testing, revision, and refinement within the scientific process. The concept of the universe's origins was first introduced in 1927 when scientists discovered that the universe is expanding, implying that it began from an infinitely dense point and has been growing ever since. At the time, The idea of a universe with both a beginning and an end seemed inconceivable to many. Even today, science still struggles to fully accept this concept. Nevertheless, it is essential to remain open to such possibilities, even when new discoveries challenge long-standing scientific beliefs. History has shown that scientific knowledge is always subject to revision. For example, in Einstein's youth, it was widely accepted that stars and planets held fixed positions in space. Today, we know that everything in the universe is in motion. Planets orbit stars, stars move through galaxies at tremendous speeds, and entire galaxies drift through space with their ultimate fate uncertain. This realization has overturned centuries-old beliefs and reinforces the necessity of continuous scientific inquiry and adaptation. Today, scientists must embrace inconsistencies and recognize that theories are never fully complete until they are thoroughly tested and validated with observational data. The Big Bang theory, for instance, arose from observations that galaxies are moving away from us, with the distance between them increasing in proportion to their separation from Earth. This theory, known as Hubble's law, was further supported by evidence such as cosmic microwave background radiation and the redshift of distant galaxies. However, it is important to remember that, in the past, people believed the Earth was flat and that the Sun revolved around it, ideas based on the best available evidence of that time. Technological advancements have since revolutionized our understanding of the universe, and we now find ourselves in a similar situation as new data from the JWST challenges some of our previous assumptions. This scenario illustrates the ever-evolving nature of science, where experts must remain open to new findings while re-evaluating established theories in light of emerging evidence. The surprising discoveries from the JWST challenge are current cosmological understanding, prompting a reassessment of long-established models. Scientists heavily rely on redshift measurements to estimate the distance and velocity of celestial objects. Redshift refers to the shift in light's color as the source and observer move relative to one another. For example, when a distant light source, like a star, moves away from us, its light shifts toward the red end of the spectrum. Conversely, when it moves closer, the light shifts toward the blue end. This phenomenon provides crucial data on the motion and distance of galaxies. However, even minor errors in redshift measurements can lead to significant consequences. As a result, many traditional assessment methods are now under scrutiny due to the new findings made by the JWST. These recent discoveries encourage scientists to reassess whether these results can be attributed to errors in redshift measurements or if some researchers are overlooking current data. This issue requires careful examination and thorough review of both the data and the methods used. Ongoing evaluation is essential, reflecting the growing recognition within the scientific community that persistent inquiry is critical to advancing our understanding of the universe. The JWST's discoveries serve as a reminder that the academic community must remain flexible, willing to challenge long-held beliefs, and adapt to new evidence. Scientific progress is driven by the willingness to revise outdated theories based on new data, and the JWST's findings exemplify how a single breakthrough can prompt a re-evaluation of the fundamental principles of our understanding. One of the most exciting aspects of the JWST's discoveries is the potential for future breakthroughs in our comprehension of the universe's fundamental structure. The telescope's ability to peer deeper into space and capture light from galaxies billions of light-years away has opened up new opportunities to study the universe's earliest moments in greater detail than ever before. The data obtained from this research will help scientists refine their models of galaxy formation, explore the role of dark matter and dark energy in shaping the universe, and gain further insights into the forces governing cosmic evolution. As we move forward, it is essential to recognize that science is an ever-evolving field, always open to groundbreaking ideas and possibilities. As we move forward, it is essential to recognize that science is an ever-evolving field, always open to groundbreaking ideas and possibilities. The discoveries made by the JWST have introduced new challenges that must be addressed, yet they also present an opportunity to refine and expand our understanding of the cosmos. While some scientists remain skeptical, others recognize that breakthroughs like these are precisely what drive scientific progress. The ability to question long-standing theories, test new hypotheses, and remain open to alternative explanations is what has allowed humanity to advance in its pursuit of knowledge. The JWST's data has sparked renewed interest in cosmology, prompting scientists to revisit fundamental questions about the nature of the universe. If these newly discovered galaxies truly exist as observed, they could signify a fundamental shift in how we understand the timeline of cosmic evolution. This could suggest that galaxy formation occurred much earlier and at a much faster rate than previously assumed. Such a scenario would require a reassessment of the factors that influenced early star formation, including the role of dark matter, gas density, and cosmic inflation. For decades, astronomers have relied on computer models to simulate the formation of galaxies and predict their characteristics. However, the existence of these massive, ancient galaxies poses a significant challenge to those models, which struggle to explain how such structures could have formed so soon after the Big Bang.